what we're going to talk about today is the geometric series. Now the geometric series is a little bit different from the arithmetic series. You can see that what I've listed here is a geometric sequence. Now remember that because it's a sequence, they're just a list of terms separated by commas. And in this case, they're terms from a geometric nature. That means that we have an R value of 3, a common ratio that we're timesing each previous term by, producing the next term. Now this is a sequence. Let's make a series. Okay, just like we did with the arithmetic series, we simply start adding the terms together and we can get partial sums. So the sum of the first term would just be 2, sum of the second, 2 plus 6, or 8, sum of the third, 2 plus 6 plus 18, which is 26, and so on. Now, my goal here is to develop a formula for a partial sum of n terms, and that's what we're going to try and develop now. I'm going to use a couple of little tricks to do it. I'm going to make a little bit of room here. So how do we develop partial sum formula? Well, I'm going to use a few sneaky tricks here. I'm going to start off by listing n terms. And since these are based on a geometric sequence, our first term is a, the second term would be a times r, the third term would be a times r squared, and so on, until the last term is a times r to the n minus 1. Now that might be a little bit crammed there, so I hope that's clear. The last term is a times r to the n minus 1. What I'm now going to do is multiply both sides of my equation by r. So I'm going to produce a new equation, r times s sub n, and the first term would become a r, the second term would be a r squared, and so on until we get to the last term, which is going to be a times r to the n minus 1 times r again. Now just to show you what this term looks like, if you're a little rusty with your exponent laws, here's what we're doing. Remember that what that means is the exponent of r, which is 1, gets added to this stuff over here, to this exponent here. And so what we're going to get is a times r to the n minus 1 plus 1, which is r to the n. So I'll just get rid of that there. So here's what we have now as our second equation. Now what I'm going to do is I'm going to go ahead and subtract these equations. So I'm going to have on the left side, let's put a little line here, so we're subtracting s sub n minus r times s sub n. And here a funny thing happens. If you think about it, all these terms are being subtracted. I'll put a sort of a negative in front there. So you're going to have a times, well, there's no like terms, so you're still going to have a. But ar minus ar cancels. Ar squared minus ar squared cancel. And this will happen all the way along. All of these guys here are all going to cancel off with these guys here, except the last one. There is no ar to the n that cancels with this. So we're simply going to be left with minus a times r to the n. Now I do a little bit of factoring. There's a common factor here, which I'm going to factor out, s sub n, and then I've got 1 minus r. And over here I can factor out the a, 1 minus r to the n. And to solve for s sub n, I just divide by 1 minus r. So I have this as a formula. And it's a very helpful, very handy formula. This is how we find partial sums without having to go through the monstrous task of adding up all the terms. we simply need to know the first term A, how many terms we want to add up, and what's R. Pretty quick, pretty simple. Let's look at an example. And this example is going to work with a ball dropping. So we've got a kind of a real-life situation here. Let's make a little room on the board. Okay, so this is going to be a ball dropping from 10 meters, and it's going to bounce up to 60% of the height that it dropped from. Okay, its previous height, and then it drops by to only 60% of that previous level. So we've got an initial height of 10 meters, and we've got this ball traveling down 10 meters. So I kind of like to draw a little visual to get a feel for it. And then what's happening is, when it bounces up now, okay, the height that it bounces to will be 60% of 10. The fast way to calculate that is to just go 0.6. Well, I don't think you'll see that. I'll draw a little bit bigger here, put it underneath. 0.6 times whatever this previous height was, which is 10. And of course, we're also going to have that ball traveling the same distance back down. So at this location, I'm going to times it by 2 because it's going both up and down. The next location here, it's going to go up again, but now it's going to be 60% of this previous height. So it'll be 60% of the 0.6 times 10. And of course, that's the height, but it's going to go back down again. So that will also double. And so these are the kinds of distances we're looking at with this bouncing ball. Now let's say I wanted to know the total distance. Okay, not the distance going up and down at one particular bounce, but the total distance, kind of the key word there. Makes me right away think of using a series. The total distance when it lands the 10th time. When it lands the 10th time. That's what we're after. Now the trick here is to say, yes, I know it covers 10 meters to start with, but this one's kind of the odd man out. Okay, I want to add up all these distances for sure. But this one doesn't quite fit the way these ones do as part of a series. So I'm going to leave the 10. Now I have to keep that in mind that I have to add that in at the end, but I'm really going to start right here. This is where I want to start looking at the terms. And the big question is now, how many terms, how far do we go? Well, it depends what, you have to interpret when it lands the 10th time. So here it hits the first time, goes up and down. So this is when it lands the second time. Okay, it hit once, went up, and it hits the second time. So to me, that's when it hits the floor the second time, that counts as your second landing. This, therefore, would go up and down, would count as the third landing. So how many terms do I want? If I'm starting at this level here, I'm counting this as my first term, I actually only want 9 terms. So that's really important. Okay. So 9 terms would correspond to 10 times that it hits. Basically stopping at the 10th time it hits. So what do I have to do here as far as this series is concerned? Well, this is going to be my first term. So I have 0.6 times 20. And if you like to, you can work that out. But I'm just going to write it like this and say it's 0.6 times 20. Oh, this is adding. The second term is going to be 20 times 0.6 times 0.6. So what that really tells me here is that R, another very important aspect of this, R is 0.6. Okay. The only other thing that I need, therefore, is what A is. And A is this value here. So that's going to be A, and 0.6 times 20. Oh, and I missed the times 2. Oh, no, it's worked into the 20, sorry. 0.6 times 20 has the 10 times 2 woven together. Almost missed that myself. That works out to be 12. So there's my first term. So now, all I have to do to answer this is go back to the formula. Now that I've thought it all through, analyzed the question, come up with A, R, and N, all I have to do is say, well, it's the sum of 9 terms, and my first term here has a value of 12, then times that by 1 minus R, and R is 0.6, raised to the 9, all over 1 minus R, and that just has to be worked out on a calculator. I did that ahead of time, and there's one more thing I have to do. Remember, don't forget to add the 10 meters. So if you do that, be careful on your calculator, you should get 39.7 meters as our answer. That's the total distance that the ball travels when it lands on the floor the 10th time. Okay, so that's an example of using our series for a geometric sequence, or based on a geometric sequence, our formula for the series, putting it to good use. Okay, now one more example, because of course we can always ask for different things and try to make it a little bit trickier. This time the question is going to be sort of phrased a little differently. So in this example, we want to find the sum. Now, sum of what? Well, let me show you what I had thought would be a pretty good series here. 5 plus 20 plus 80 plus ... all the way up to 20,480. So we're going to attempt to find this sum out. Now you'll notice a couple things here. First of all, no problem. I got A, that's 5. I can get R pretty quickly by asking myself 5 times what gives me 20. So I think that's pretty easy to spot. R is 4. Where the problem kicks in is I look at all I need is N, and I don't know. So what I'm going to have to do is figure out which term is this. Is this the 12th term, the 14th term, the 30th term? Okay. What I'm going to have to do is say, well, what's a formula for a geometric term? And use that. Well, that formula looks like this. A times R to the n minus 1. So I can give myself a little bit of room up here, figure out what that term is. What I'm basically solving for now is n. So I have to do this. I guess I'll start down here because I think there's going to be a fair bit of room needed here. So I know the value of the term, 20,480, and that equals A, which I know is 5, times R, which I know is 4, to the n minus 1. So what I'm after is I want to solve for n. So I'm going to start this process by dividing both sides by 5. And so this left side here turns into 4,096, and that'll equal 4 to the n minus 1. Now I'm probably losing the space here, so I'm going to continue at the top. What I'm going to do now, try to get n here, I'm going to take logs of both sides. So I'm going to take log of 4,096, and that equals, and bring down the exponent, n minus 1 times the log of 4. Now remember that log of 4 is just a number. So I'm going to divide that over to this side. So I have log of 4,096 divided by log of 4. And that would equal n minus 1. So I just add the 1 over to here. And this is handy for me with this little eraser here. There we go. There's n. And if you work that out, n turns out to be 7. Now all I have to do to find my sum, and I'm going to go back to here, say, well, we figured it out using this formula, give myself just enough room for the easy part. The easy part's just a matter of, we're going to use our formula, we're adding up 7 terms, so a, which is 5, times 1 minus r, which is 4, to the n, which is 7, all over 1 minus r. And I went ahead and did that, and I got 27,305 as the sum of all of these terms. And rather an interesting thing that, we've got 20,480, and all these little small numbers, all they do, all these previous terms, is they sort of push it up about not even 7,000. It's kind of interesting how that's a pretty big term in value. And with that, ladies and gentlemen, that's our look at geometric series, and we'll catch you later.